So let's assume now that we have a cylindrical shape. So we have a pipe. When I say a pipe, which means that it has an inner hollow space and it's allowing for a fluid or something to flow inside. That's a pipe here. That pipe has a length of L. Let me draw the center line of that pipe. I'm going to have R capital I standing for inner radius. I'm going to have an outer radius, R capital O, right? That thickness is a solid, so I have a thermal conductivity of that made stainless steel, copper pipe, whatever it is. So I know now, if I keep the interface of that pipe somehow at a high temperature. So this presenting the surface temperature inside the pipe. I keep the outer surface of the pipe at lower temperature. Do we have a driving force? Yes, we have a temperature difference. What's going to happen? Energy has to transport. From where? From the high temperature phase to the lower temperature phase. So I know that I'm having energy going radially in all direction between the inner phase to the outer phase. Remember, we keep TH for the whole phase, inside phase. TL is for the whole outside phase. So energy is going from each point inside to the each point outside. And this is total of that is Q. And this Q is going by conduction. Why? Because it's going through a solid material. So how do we simplify a three-dimension drawing related to the cylinder? Very similar to what we did with the plane surface. And instead of drawing cubical shape, we're going to actually do a simplified drawing for this case here. So how we simplify that? I draw a center point. Then I know that I have two radii. So I have, this is presenting our inner. That curvature here is presenting our out. That interface, that presenting the interface of the tube, I'm going to put here TH. Then this is presenting the outer face of the tube that at lower temperature. And this is totally a solid material with thermal conductivity K. Okay? That's how we simplified this. Recall the three-dimension drawing of the plane surface. Just to refresh your memory. This is thickness L. This is solid body at thermal conductivity K. The back face is at TH. The front face here as TL. So we simplified that by two parallel lines separated by a distance L. This face has higher temperature TH. This face has a lower temperature TL. And we know that thermal conductivity is here. There is energy going to transfer that direction. That's Q. There is energy is going to transfer that direction. This is Q. In a simplest form, we were able to assume the temperature changed linearly here, and we write Fourier's law, right? So we assume that temperature changed linearly here. So the governing equation was originally what? Q is equal minus Ka partial T by partial X. What is X is this direction here. Okay? Then we simplified that to be Q is equal Ka TH minus TL divided by L. And we simplified that more to have Q is equal to delta T over the thermal resistance, right? And we presented that by a thermal resistance between TH, TL, and this is R thermal. And R thermal can be calculated from L over Ka, and there's Q going through this. So this is all what we did for plane surface, correct? Now, let's try to do that for the cylindrical one. Just adjust the camera so we can include most of the content in one view here. Okay. One would say, hey, what's the governing equation first? Q is equal minus Ka partial T by partial R. Because Q is going in that direction. R is the vector that's going in this direction. So Q is moving in the R direction. Okay. Can I assume that temperature changed linearly here? No linear change. So that assumption is not valid here. We can prove that, but it's going to be too much time to take for that proof, and it's beyond the course content. One would say, hey, what about if we assume this looks like a plane wall, and there is TH in here, there is TL in here, and the thickness here is the difference between R out minus R inner, and this is K here. I can say that Q that's going in here can be calculated from K A TH minus TL divided by RO minus RI. All what I'm going to do, I'm going to say this is wrong. Everything here is based on a linear temperature distribution assumption, which is not valid here. So this is a very common mistake that students, if you do that, I know that you didn't get anything out of this course. And mostly you're going to lose big grade of that course. So be careful. When we deal with cylinders, things are different, okay? Things are totally different. So this assumption cannot be valid here. I cannot use it, okay? But still, this assumption is still valid. Q is equal delta T between this surface and this surface divided by the thermal resistance. So I can present this guy here. I can present that cylinder here by the following. Two nodes, TL, TH, and in between, there is a thermal resistance. That's what type of thermal resistance? What's happening inside that solid? It's conduction. And there's Q going through that resistance. Very similar to this. It's still valid. But the point is how to calculate the thermal resistance for that case. In this case, I'm not going to drive this equation. It takes longer time. So I'm going to give you the equation and you are allowed to use it. R thermal conduction in the case of the cylinder is equal to natural log of the outer radius divided by the inner radius, that's a ratio, divided by 2 pi KL. So this is given to you right now. It's a natural log of the ratio of the outer radius to the inner radius. And this has to be greater than 1 because natural log of a fraction is negative, cannot happen. So be careful. It's R out over R inner divided by 2 pi. K is the thermal conductivity of the metal of that cylinder, and L is the total length of that cylinder. So that's the conduction thermal resistance. This is equivalent to this for plane wall. Okay? So that's given information, good to go and use it. Remember this was conduction, right? In the plane wall, what was the R thermal convection? It was 1 over H times the surface area. That's for plane wall, right? This equation is still valid for cylinder 2. So R thermal convection is equal to 1 over H times the surface area. Just keep in mind, let's assume that there is a convection happening from the outside face of that cylinder to a fluid at T infinity and H. What is that contact surface area between this fluid and that cylinder? It's going to be the surface area of the cylinder. Usually we ignore the sides, guys. Don't count for the sides when you deal with convection that way, unless it's specified in the problem. But usually the surface area here is 2 pi RL, or it's pi DL. But the question is, which radius I should use? It depends. If the convection is happening inside, so the convection is happening with the inner radius. If the convection is happening outside, the convection is going to be happening with R out. So if you took outside, like this case here I'm explaining here, this will be R out. Okay? Or its outer diameter for that one. So this will be the equation for the convection heat transfer resistance in a cylindrical shape. Again, remember, there is no internal heat generation. Everything is steady, so we're still solving very simple heat transfer mechanisms here. Okay, so I'm adding up as we go. So what would be the most complicated case here? Most complicated case like I have a pipe. I'm not going to draw 3-dimension anymore. I have a pipe. So any pipe has inner radius and outer radius. But this pipe is wrapped by thermal insulation. So that's the pipe. That's the pipe wall. That's insulation. So I'm going to have a third radius, RS, which is the insulation radius. Okay? And let's assume this is actually a pipe that carry steam inside. So inside the pipe, this is where the flow is happening, right? So I have a steam here. So I have a fluid that has a very high fluid temperature, T infinity 1, and it has a convection heat transfer coefficient. I'm going to call that H inner, the inner heat transfer coefficient. Then the outer face of the insulation is exposed to the atmosphere where the ambient temperature is T infinity 2, and there is a thermophysical property for the air outside that's called H2. I'm expecting steam is at highest temperature, the ambient air is the lowest temperature. How are we going to present that problem here? Again, I know for sure all the heat is going that way. It's going to go from the steam to the inner face of the pipe. It's going to move from the inner face of the pipe to the second layer of the pipe. It's going to move from the second phase to the third phase, and it's going to leave from the third phase to the atmosphere. What mechanism is that? Convection. How did you know? It's between moving fluid and the solid surface. What's mechanism here? Conduction. Why? It's going through a solid layer. This is the pipe body itself. What mechanism here? Conduction. How did you know? It's a solid material, which is insulation. What's happening outside here? Oh, that's convection. It's heat given to a flowing air outside. Even it seems to be stagnant, but there is a gas motion. There is a fluid motion out. Okay, so, and what's happening? I know that T infinity 1 is much, much bigger than T infinity 2. So I know that temperature is decreasing that way. I'm going to label that phase by T inner. I'm going to label that phase by T out. I'm going to label that phase by TS. So I know that T infinity 1 is greater than Ti. Ti is greater than T out. T out is greater than T surface. T surface is greater than T infinity 2. Okay, how to present that problem in a thermal circuit analysis? Very easy. Count the temperatures. I have 1 here, 2, 3, 4, 5. I'm going to put 5 nodes. T infinity 1 is here. T inner, I'm going to call it here. T out is here. T surface is here. T infinity 2 is here. That's T infinity 1. That's Ti. That's T out. That's T surface. That's T infinity 2. Between each 2 nodes, you got a resistance. So let me use different color here. So what we're going to have? We're going to have 2, 3, 4 resistance. Each resistance presenting a mechanism of heat transfer. The first one is convection. Conduction. Conduction. Convection. I'm going to label them R1, R2, R3, and R4. These are a set of series resistance. I know that the heat going from the steam to this phase is the same quantity to this phase. It's the same quantity to here, same quantity outside. Why? Because it's a steady state. There is no energy stored, and there is no internal heat generation mentioned in that problem. So I know that I'm having one single value of Q going through all of these resistances here. Okay, so now let's do the calculation. Let's do the math. How we calculate R1? Remember, what we are solving, this is not plain wall. This is cylinder. It just simplified in a 2-dimension drawing. What is R1? R1 is convection. What is the equation for convection? It's 1 over H times the surface area. That's the equation. What is the surface area? I'm talking about the convection happening between the fluid, the steam, and this phase. So this is the surface area I'm talking about. What is this surface area? It's 2 pi r L. What is L? It's the length of that pipe. Which radius we're talking about? The convection here is happening with Ri, so this will be Ri. What about R2? R2 is conduction. Let me write down the general equation for the resistance conduction. R thermal conduction in a cylinder, it's equal natural log of the outer radius over the inner radius divided by 2 pi k L. This is a general equation. Let's apply this equation. R2 is between Ti and T out. R2 is here. R2 is presenting this solid body here. So what are the boundaries here? Ri and R out, right? So that ratio will be natural log of R out over Ri divided by 2 pi. I'm going to assume the pipe has the thermal conductivity K1, so I'm going to call that K1 times L. Now, let's do R3. R3 is conduction. This conduction is happening through this wall. What are the boundaries of this wall? It's R out and RS. So I'm going to pick the outer radius divided by the inner radius. Outer divided by inner. The outer is RS. The inner called R out. Divided by 2 pi. Then I'm going to add thermal conductivity for the insulation, K2 times L. Then the last one is convection. R4 is convection, which is equal to 1 over H surface area. We call the H here is HI. We call the H out there is H2 or H out. Let's call that H out actually. Now, what about the surface area? It's 2 by RL. Which radius? The convection here is happening with RS. The fluid is touching the RS, so that's RS. Now, you can calculate all the resistances. Again, I'm going to force you by giving only this temperature and this temperature. So if you want to calculate Q, how are you going to do that? Q, you pick any delta T, you divide by the resistance in between. Since I'm only giving you T infinity 1 and T infinity 2, this is the only temperature difference that you have. You have to divide by the summation of all the resistances here. So that's R1 plus R2 plus R3 plus R4. Then I want to calculate Ti. Again, you're going to take that value of Q you calculate. You're going to do that calculation again by T infinity 1 minus Ti divided by R1. This equation can easily get me Ti. I want to get T out. I'm going to take the same Q. I said that's equal T infinity 1 minus T out. In this case, I'm going to divide by R1 plus R2. This equation will give me T out. I want to get TS. Don't take the long distance solution here. Go for the short one. I will take the same Q and say it's equal T surface minus T infinity 2 divided by R4. Simply, I can get T surface out of this equation. So I was able to calculate Q and the interface's temperature for this problem. Without thermal resistance, what are the governing equation here? For conduction, it's minus Ka partial T by partial R. That's for the first layer. Second one, minus Ka partial T by partial R. That's for the second layer. There's convection, Ha delta T for the convection here. And there is Ha delta T for the convection here. How are we going to solve this equation together to get the solution? It was easy in the plane surface because it's all a system of linear equation. Now I have two differential equations here. And I don't know what's the temperature as a function of R. So that was impossible here. There is no way you can solve that problem without going into differential equation and boundary condition and things like that, which is very complicated, which we focus on this for people taking heat transfer courses and things like that. But again, for the purpose of this course, I don't want to complicate things. So thermal resistance is a magic solution, especially for cylindrical shape here. The last geometry that I'm interested in is actually the spherical shape. So let's look to the spherical shape, sphere, and provide you with the two equations for the conduction and convection resistance. So let's do the sphere. again, it's a hollow sphere, so it's empty from inside. So when I wanna present that, I'm gonna present it the same way as cylinder as well. But I know that each curve here is presenting a surface of a sphere. This is the inner radius of the sphere. This is the outer radius of a sphere. Think about hollow sphere, right? The beauty about hollow sphere, there is no flow inside. It's enclosure, right? There is no way to have a flow inside, right? So basically, the sphere will be maybe exposed outside for a fluid, but there is nothing inside here. Okay, so let's assume that the inner surface here is really very high temperature, TH. The outer surface is TL, and there is a convection outside. So I know that there will be a conduction going here, and there is a convection going here. That's conduction. That's convection. No internal heat generation inside the sphere. It's a steady state problem. So what's in is what's out. What are the equations that we're going to need for a spherical shape? We need two equations. One for the conduction resistance and one for the convection resistance. For the conduction resistance or thermal conduction, the equation is 1/4 pi K, where is K the thermal conductivity of that thickness, that's a solid material, multiplied by 1/, the inner radius minus 1/, the outer radius. Inner radius is smaller. You flip that number, this number will be bigger than this number, so it's going to end up to be positive. So that's the equation. What about the convection? Our thermal convection is still the same. It is 1/h times the surface area. In this case, what is the surface area of a sphere? 4 pi r squared, which r, the convection is happening with the fluid is in contact with the outer radius, so this would be our out square. So that's the convection. How are you going to present that problem here? Very simple. How many temperatures you have? 3. TH, TL, T infinity. Let's do it actually here. TH, TL, T infinity. TH, TL, T infinity. How many resistances you have? 2. R1 is conduction. R2 is convection. I have Q going through. How you calculate R1? R1 will be this equation here. 1/4 pi K, 1/Ri minus 1/R out. And R convection R2, 1/4 pi R out square H. Then you want to calculate Q. I'm going to give you this temperature and this temperature. So it will be TH minus T infinity divided by R1 plus R2. Then you take the same Q and say that's equal to TH minus TL divided by R1. This will give you the interface temperature TL. Very simple. Very simple. Okay. So if I want to summarize all what we covered so far, I can write down all the resistance as follow. And when you go and check the slides of that lecture here, you'll see that there is a table. It's summarizing all the resistances that we're going to need to solve the homework and things like that. You don't have to memorize them. Have them next to you when you do the homework, but they are very crucial and very important for quizzes and exams. So I would say the following. I have plane surface, we have cylinder, and we have sphere. We have conduction, and we have convection. The thermal resistance for plane surface, conduction, it's L/Ka. The convection is 1/Ha. What about cylinder? Natural log of the ratio of the outer boundary to the inner boundary divided by 2 pi Kl, and the convection is still 1/Ha. Sphere, it's 1/4 pi K multiplied by 1/, the inner radius or inner boundary minus 1/, the outer boundary, and still the convection 1/Ha. This is just A. Here, that's going to be 2 pi RL, depending which radius we are talking about, inner or outer, could be I, could be out, depend on how many convection you have. For the sphere, is going to be 4 pi r squared, which is the surface area of a sphere. This is the surface area, cylinder surface area. And this is sphere surface area. So that's all the resistance that you're going to need. Q, you simply select any delta T divided by the resistance in between. Or if you want to get the, that's calculating the resistance, by the way, right? This is R, this is R thermal, R thermal, R thermal, R thermal, but convection, R thermal, convection, R thermal, convection. Then use this R thermal with any delta T to get Q, or use Q to calculate any other interface temperatures as needed. So that simply summarize the thermal resistance analysis for plane wall, cylindrical shape, and spherical shape, and how we apply that in a quick and easy way to do the analysis to calculate the rate of heat transfer, or to calculate any interface temperatures as well. So before we move forward to the next level of energy transport, let me recap here about the thermal resistance, and maybe kind of a trick that you may see in a problem or something like that. So, and it's a good exercise as well without numbers, but it's a good exercise here. So let's assume that I give you this schematic here. And these are 4 blocks. These 4 blocks, they have, let's say that this is L1. This length here is L2. And this length here is L3. Let's renumber these blocks. That's block number 1, block number 2, block number 3, and block number 4. And let's assume the height of that small block is half the height here, and all of the blocks, they have the same depth to the page, right? So that's a geometry here. They are made of different materials, so that's K1, K2, K3, and K4. And let's assume that I have a fluid that's touching that face with T infinity I and HI. I stand for the inner face. And in the outside here, I have T infinity out and H out. And let me assume that T infinity I is much, 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 much higher than T infinity out. So if there is any temperature difference, we should have thermal energy transfer. So I know that energy has to go from this way to this way, right? So what's going to happen is I'm going to have energy going from that fluid to that face of the block combination here. So let's call that face here, temperature is T1. Then T1 will drive that quantity of energy to go through that block number 1. So energy will go all the way to this face here, right? I'm going to call the temperature of that face T2. Okay? Then energy has to split, not equally, but they have to be divided, right? Why? Because I have block that's made of copper, and I have a second block that's made of concrete. It's impossible that energy will split equally between 2 different materials. One of them has a higher thermal conductivity. So energy will divide partially at the top and partially at the down, but still the summation of these 2 parts should equal the total energy that was actually sitting on that face. Then all the energy that's splitted, they're gonna meet again at that face. Let's call that face T3. Then now all the energy will be driven through one more block all the way to the other face here. Let's call that face temperature is T4. then energy will leave to the coolant on the other side. Now, how many mechanisms of heat transfer we have here? We have convection, we have conduction, we have conduction up here, we have conduction down there, we have conduction here, then we have convection here. Now, think about the energy that's going through these blocks as electric current. What's going to happen? First, I have T infinity I. I'm going to put a node here. I'm trying now to draw the thermal circuit of that problem. T infinity I is here. I will have T1, I will have T2, I will have T3, I will have T4, I will have T infinity out. So this is T infinity out, this is T infinity in. Now, between T infinity in and T1, what happened? I have the whole amount of energy transported by convection. So I will have a resistance here. I'm going to call it R1, and this should be convection. Now I'm standing up here. What's going to happen between here and T2? Between T1 and T2, all the energy will be driven by conduction. So I will have a conduction in a series with R1 because the total energy will continue at the same resistance. So these are series resistances here. That's conduction. Now, the energy at phase 2, right, has to be divided. When the electric current get divided, these are, that's correct, parallel resistances. So what I'm going to do, I'm going to break down the energy into 2 parallel resistances. Each one of them is conduction. I'm going to call that R2. Let's call that Ri. Let's call this R1, just to be consistent with the block numbering. That's R2. I'm going to call that R3. So the total energy that was going through these resistances is going to break down into 2 parts. Quantity will go up to the resistance R2, and the lower the resistance, the more the energy that you're going to get into that resistance. And the second part will go down there. Then both energies will meet again at this point here. So that's presenting actually T3. Then the whole energy that going through Ri and R1 will continue on the other side. So this will meet again. We will collect the 2 parts of energy here, and we will go through the block number 4 with a resistance 4. This is conduction resistance. The lower one is still conduction resistance. Then R4 also is a conduction resistance. Okay. Then the total energy reach out that phase T4, right? This is T2. This is T3. Okay. You can actually shift the node a little bit here and say, okay, this is T2. And I'm just having like this. I'm going to shift that node here and close the circuit here. And this is T3. Either way, doesn't matter. Then the whole energy will go for the loss, go through the loss resistance, which is R out, which is actually a convection. Okay, so now I transformed the problem into thermal circuit analysis. Now, how to calculate Ri? Ri is E convection resistance, so that's going to be 1 over Hi times A. Go back and recall R convection. Remember, this is plane wall, so it's 1 over Ha, or surface area, and R conduction is simply L over Ka. I'm just writing down the formula here without specifics. So let's apply these 2 formulas for all the resistance here. So Ri is a convection resistance, 1 over Ha. The area I'm talking about here is this height times the depth. Keep in mind, it's always the area perpendicular to the heat flow. So it's going to be the height here, whatever that height is, H, whatever it is, times the depth. Now, let's go to the conduction for that block. The block here has the same height all the time. It's uniform height. So R1 will be L1, that's the length of that block, divided by the thermal conductivity of that block, K1. Here we have A, and here we have the same A, because the height for convection is the same height along that block for conduction. Now, let's go for R2. This is conduction. The length of this block is L2. The thermal conductivity of the upper block is K2. Now, the height is half the total height. So, and the depth is the same, which means that I'm getting half of the area. So this will be actually A over 2. Same apply for R3. The lower conduction resistance is going to be L2. The length of block 3 is the same as L2. K3, and the area is half the area because the height is half the height. Now R4 is, and now I'm going back to the total height. So I'm going to have the block 4 has a length of L3 divided by K4 times the total area. I went back to the total area. The loss resistance is for the convection outside, which is R out. R out is 1 over H out. I'm still having the total area. So now, if you know all these variables here, you can calculate the resistance. Now, if you want to calculate the heat transfer, Q. If you want to calculate Q, you have to pick 2 temperature difference and divide by the resistance in between, right? So let's assume that you are only given T infinity I, or T infinity here, and T infinity here. Which means that if you want to calculate Q, the only option that you have is T infinity I minus T infinity out divided by the equivalent resistance between these 2 temperatures. So what's between these 2 temperatures? Ri, R1, these are series. R4 and R out are series. These are parallel. You have to get the equivalent of this. So I have to remove these 2 and just having an equivalent resistance here. I'm going to call that Rx, where I can add all of these resistance together. So this should be Ri plus R1 plus Rx plus R4 plus R out. Where is Rx? How to get the equivalent of 2 parallel resistance? It's the multiplication over the summation. So now I can calculate Rx and go back here. I can get all the quantity of Q. So I can get Q out of this equation. If you want to get T1, go back to the last recording. I can take the same Q and I say that's T infinity 1 or I minus T1 over Ri. What you are getting out of this, I can get T1. You take the same Q equal to T infinity I minus T2 divided by Ri plus R1. I can get T2. And so on for T3. But for T3, you don't have to go this direction. You can take T3 minus T infinity out over these 2 resistance. You can get T3 and T4. One extra question you may be asked. How much of that total Q actually went up here? Q upper and Q lower. How much of that total Q, because we know that Q is going to split up and down. Okay? And if you get one of them, you subtract that from the total Q, you can get the second. How to get that? You guys think about it. Go back to your circuit analysis and see that if you want to get the Q up here, okay? If you want to get the Q up here, there is a relationship between Q upper, Q total, R2 and R3, okay? So the current in a branch is related to the total current by a ratio of these resistances here. So think, please go ahead and think how to calculate Q upper by using Q, R2, and R3. Then if you got Q upper, I know that total Q should equal the upper portion plus the lower portion. I applied the node voltage application here. I'm sorry, I'm speaking circuit analysis, but these are very fundamentals. It shouldn't be a complicated thing. The current going through a node is equal to the current going out. Energy conservation, right? Q in, Q out. Energy in, energy out, right? There is no energy generation. There is no transient. I mean, everything is a steady state. So if you know how to get Q upper, you subtract Q, which you did calculate here. From that Q, you can get Q lower. So that could be the most sophisticated problem you could see in maybe in a quiz, in a homework, things like that. But I thought it's also to share with you the case when the thermal resistance could be in parallel. Not all of them are in series. And that was a good example I found to share that with you guys. Now we can move to the next part.